This is section 5.3. We're going to use angle bisectors of triangles. We need to remember that an angle bisector is a ray that divides an angle into two congruent adjacent angles. So here's an angle. If this ray bisects the angle, the big angle, then these two little angles are congruent. That's what these marks are for. Remember also that the distance from a point to a line is the length of the perpendicular segment from the point to the line. So in other words, if I'm going from this point to this ray over here, you need to travel along a right angle. Don't say the distance from this ray to this ray goes on some angle like this. If you're going from this ray to this ray, you need to move along a right angle. Likewise, if you're going from this point to this ray, we're going to move along a right angle. That's how you measure the distance from a point to a line or part of a line. Okay, so in this diagram, ray PS is the bisector of angle QPR. That's how you read that geometry. And the distance from point S to ray PQ is this distance, S to Q, where these are perpendicular. Likewise, if you want the distance from point S to ray PR, it's going to be this distance all along this right angle. The reason we went over that is so that you understand this next theorem, the angle bisector theorem. If a point is on the bisector of an angle, like point D, then what that means is that point is equidistant from the two sides of the angle. So if you have an angle that's bisected where these angles are the same, then what do you know about these lengths here? They're going to be the same also. Now, it's important that you realize that these are right angles, because if these were not right angles, then these distances would not be the same, regardless of whether or not those were the same angle, just congruent angles. So that's what the angle bisector theorem says. If you have an angle that's bisected, so these are the same, then you know these are the same. Now, there's also the converse of the angle bisector theorem, and that's theorem 5.6. What that tells you is, let's say you have this angle where there's a point that's on this ray, and this point is the same distance to this ray as it is to that ray. Now again, you got to have the right angles. If these are the same, then what do you know about these angles here? Well, these angles are the same, or the big angle is bisected. Okay, so we'll try an example. Let's use the converse of the angle bisector theorem. Here you have an angle. Here's a point J that's on a ray. This point J is the same distance to this ray as it is to that ray. So you need those right angles. You obviously need those marks. If this angle is 42 degrees, what's the measure of angle JFJ? It's also 42 degrees. It's a very, very simple theorem. This triangle is congruent to this triangle. Let's solve a real world problem. A soccer goalie's position, that would be G, is relative to the ball and the goalpost, and the shooter, or the striker, we're calling S, has congruent angles. So the goalie is placing himself or herself in this line of fire where this angle is split between the goalposts. Will the goalie have to move farther to the right goalpost or to the left goalpost to block a shot from the striker? Well, if the goalie's doing this right, the goalie's not going to move to the goalposts. What the goalie's going to do is move perpendicular into the path of the shot. So the goalie wants to move this way, not this way. It's quicker to get into the path of the shot this way than it is to go that way. Same thing to defend a shot going this way. You better form a right angle with the line of the shot. So you want to move this way, not this way. So the idea is, if the goalie puts himself or herself in the correct position where you're splitting that striker's angle, what do you know about these distances? They should be the same. Now, obviously, if the goalie misplays it and tries to move towards the goalpost, that might be a little bit further than moving to this goalpost. Okay, but we're not sure, depending on what position the goalie's in. But if the goalie plays it right, you should split that angle and have equidistances to move to block the shot. We're going to use algebra to solve a problem. For what value of x does point P lie on the bisector of angle A? So here's angle A, and we want point P to be on the bisector of angle A. So we could just draw that bisector in there. Now, that's not a bisector yet, but to be a bisector, you would need those to be congruent. Well, if those are to be congruent, what would you have to say about these distances from P to B compared with P to C? That distance from P to B better equal the distance from P to C. As long as these are right angles, these need to be the same. So I'm just going to switch this around because I want to solve the equation like this rather than the other way. So I'll just use the symmetric property and flip those. These lengths must be the same. So we're going to subtract x from both sides. Then we'll add 1 to both sides. That's the value of x. That's what they ask you for. Here's an angle. Notice how this angle is bisected. These two little pieces are the same, so the big angle is bisected. What do you know about these distances along a right angle? They better be the same. 4x minus 6, 3x plus 5. You don't know what they are, but they need to be the same.